Hello, Tibra.
How are you? Can you
I'm
hear me?
I'm good. How are you?
I'm all right, yeah. Thank you for helping me change the time.
No, thank you for adjusting it in your schedule.
No, it's my pleasure, yeah. So,
Yeah, we'll just wait a few minutes and then we'll start.
yeah, of course.
So Tibra, I was curious, like, is it a summer semester going on there?
Yes, we have 3 semesters. They're actually
Like, is
trimesters.
it a like in Pakistan, the summers is usually for students who are repeating a course and like it's not a regular semester, it's shortened also. So is it the same or it's a regular semester
It's a regular semester.
and like it is not shortened, it is same as fall thing.
No. I think like when I worked in the US, it was like Pakistan, where summer is a short semester with more frequent classes and for those who
Yeah,
want to catch up.
yeah.
But in Bangladesh, none of the private universities, or very few of the private universities, do that. Even though the government wanted them to switch to 2 semesters, and the reason is purely financial, because the private universities want to make as much money as they want, as they possibly can. So if they can do 3 intakes per year, that's more
Okay.
money than 2 intakes. So yeah, that's the reason.
All right, so I think you can start because lecture is being recorded. So
Okay, so welcome to day 2. So last time, what we did is that I reviewed the condensation of string, and then we talked about what to do with the 26th dimension of space-time in string theory, and we want to wrap up some of those dimensions in small circles, as in Kaluza-Klein theory. In Kaluza-Klein theory, the motivation was to interpret the gravitational excitation in the X-ray dimension as electromagnetism in 4 dimension, as well as but they got a scalar field for free, and that was the reason why Kaluza-Klein theory never worked. And string theory will have similar problems, and so these extra fields that string theory produces, it is a challenge to get rid of them, and that's really one of the problems that string theory is facing today. So now, if I look at the string worldsheet, the uh, the equation of motion for strings. So this is basically the written in complex worldsheet coordinates, and Z here stands for, I think, e to the power tau minus I sigma. This is a conformal transformation, complex conformal transformation, and string theory having a conformal symmetry, the physics doesn't change when you do this transformation. So this was a solution to the equation of motion, which is of this form. Now, so the most general solution to this equation of motion is we have a right moving part and a left moving part. Right? This is the most general solution to the equation of motion. And in general, you can't really say much more. That's the best we can do. To write down more precise solutions to this, one needs boundary conditions. But we are given the boundary condition in closed and open strings. In the closed string, our world sheet, as the string propagates, it sweeps out a world sheet which is cylindrical. And this is the spatial coordinate, and that goes from 0 to 2 pi. And when we're discussing the open string, so the space coordinate, it goes from 0 to 2 pi. And another thing which is important and which will come up is that, so for the closed string, the boundary condition, spatial boundary condition that we impose is that if sigma changes by 2 pi, we get back the same, right? If we are in a non-compact space. But for the open string, that is not the case. So for open string, what one does is that we introduce a normal, a Neumann boundary condition. So N stands for normal to the boundary. And this is the condition that we, just one second. Let me make sure I don't write this wrong. Yeah. So we can more precisely say that this is the boundary condition that we want for the open string. And this condition is called the Neumann boundary condition. Okay. All right, now, so these are the conditions which tell us what the precise form of these things is. Now, suppose we don't really worry so much about the boundary conditions. Now, when we have a space-time where my 26-dimensional space-time will have form of non-compact 25-dimensional Minkowski space times a circle, then of course these conditions will change. And what we'll have is that we will no longer, the left and right moving part will not have to be necessarily correlated in the usual way. So what do I mean by that? I mean that in the, so if I don't worry about the, matching the left movers and the right movers so much, because it'll depend on the context, we'll get from the left mover, we'll get a center of mass. And from the right movers, so this is the right mover, and the left mover will get another center of mass. And then we'll get the 0 point, the oscillator for the right mover and the left mover, as well as you'll get this thing. And then we'll get the oscillator terms, right? So, well, let's write the oscillator because it's very important. It'll help us jog the memory. So it's I square root of alpha by 2 sum over n doesn't cover 0, and 1 over n alpha n mu e minus 2I sigma minus, and then plus I alpha prime 2 sum over n excluding 0, 1 over n a tilde n of mu e minus I 2I sigma plus. Okay, so this is the general solution. So when we have a non-compact space and we change our coordinate on the world sheet, say from sigma to sigma plus 2 pi, that is, we come around one circle around the world sheet. You know, if you look at this, what happens is that this x mu changes. And this x mu changes, as usual, this should be sigma. So the way it changes is that everything else is periodic. So it's only this term where it changes. And it changes up to 2 pi square root of alpha prime by 2 alpha naught mu minus alpha naught tilde of mu. But when we have non-compact space, these 2 points must be the same point, right? We're coming back to the same point in space. Therefore, or space time. Therefore, this extra term must vanish. For non-compact space, we impose that, you know, this has to be equal to this, and this is what we call the momentum, the center of the mass momentum of the string. Right? So, and that really leads to the usual expression for the string worldsheet solution. So this is for non-compact spaces, non-compact direction. So when we have a compact direction, when we have a compact direction, what we have is that the the P25 operator, which is, we will call it the momentum operator, but it's actually not momentum. It's a formal momentum. And in the compact direction, you know, you have a wave function, you know, the eigenfunction of this operator is going to be periodic. And therefore, it will be quantized. So when you apply the momentum operator, which we know to be the derivative on that eigenfunction, we will get that momentum in that compact direction is quantized. So this is the 25th direction, and its radius is quantized, is r. So this is basically one of the conditions we get. We can also ask what happens to the x25 direction if I now do this. Now we saw that over here, this extra term had to be 0, but in this case, this will no longer be, they don't have to be 0. Let's see why. So we have to x25 then goes to x25 plus 2 pi square root of alpha by 2 a naught 25 minus a naught tilde of 25. Okay, so so now the idea is that as the string goes around the world sheet, as you go on the string, as in 25, 0 to 2 pi, you can go around this direction, x25 direction, more than once. Okay? So therefore, the length of x25 that you have traversed, this is really the length of x25 you have traversed as you go around the string, that number doesn't have to be 0. It can have winding, meaning that if the string winds around once, it'll be 2 pi r. If it winds around w times, then that'll be w. So w is some integer which tells us how much the string has wound around in the clockwise or the anti-clockwise direction. So this w, it's called the winding number. So we see that the winding number, which is quantized by the nature of the fact that you can only wind around something a finite number of times, an integer number of times, and the momentum, which is quantized also because of quantum mechanics. So this new thing, the winding number, we did not have in Kaluza-Klein theory. So this is a new feature that only comes in string theory because string is an extended object. Okay. So we can, of course, just get rid of these 2 pi's, and we can now consider this equation and this equation, and we can solve for alpha and alpha tilde. So if I do this, these 2 equations, lead us to alpha naught 25 is going to be n over r. This is just simple algebra. Omega r by alpha prime. So let me just make sure we can see these equations. I'll actually, let me just copy that and paste that here and make it a little smaller so it can fit. All right. All right, so from these 2 equations, we are solving for alpha and alpha tilde. So So we have square root of alpha prime by 2. And this is sometimes called the left moving momenta in that direction. But we won't really be using this terminology. And here it's alpha tilde 25. And this is going to be n by r minus omega r by alpha prime square root of alpha prime by 2. And this is sometimes called the right moving momentum. All right, so these are the terms we have. And now we can look at what the mass of the string is in the context of this new compact direction. So remember, the mass is related to the mass squared is related to the momentum through the mass shell condition in non-compact space-time, right? So this is the mass shell condition. And in non-compact space-time, this is just given by 2 by alpha prime. And then we have these oscillators, right? These oscillator modes. Yeah, these oscillator modes. These are the right movers, and here we have the left movers. And then we have the normal ordering constant, which was 1 for each direction. So we had 2 in total. So this was in non-compact space. Non-compact space. Now, when there is a, and then, you can write this as succinctly as 2 by alpha prime. This first guy, sorry, this should be like that. This first guy, we call it the n operator. It counts the number of excitations in the right moving part. And the second guy is called n bar. It's the number operator on the right moving part. And then we have this minus 2. Okay, this is the short version of it. Now, when this is m squared is, when we have a compact direction, then the mass term only now involves the first 25 dimensions, including time. Right? That's what we understand to be momentum. So what happens to the 25th term? That term goes to this other side of the equation and now contributes to the mass equation. So this is going to be plus 4 by alpha prime n minus 1. So this equation comes from L0 minus 1, this condition. So similarly, we'll have another condition, which was the other Virasoro condition for L0. So if I use that, then this is going to be, okay, let me just first write this in terms of the oscillator. So this is 2 by alpha prime, and then alpha naught 25 squared plus 4 by alpha prime n minus 1. So this thing gives us this formula. And this guy is going to give us another formula for the mass. But now we have tilde. And now the oscillator modes are going to be the left moving oscillators. Okay. So, so this is a new development. The fact that what used to be the 25th momentum is no longer, you don't think of it as part of the momentum in non-compact space-time, and therefore it doesn't contribute to what we call quote-unquote mass in the same way, but it does contribute by going on to the other side. Okay. So now that we know that what these things are, we can substitute, if you want, in this equation. So what we will do instead is that we are going to say, okay, we know the Hamiltonian. The Hamiltonian is L naught plus L naught bar. But what we are going to do is that, the Hamiltonian acting on this, basically we add these two equations to get the Hamiltonian. And of course, this acting on the state is going to be L naught plus L naught bar minus 2. Acting on the state is going to give us 0, right? And here is the normal ordering constant. So if I do this, if I add these two guys, what do I get is, I get 2m squared is equal to 2 by alpha prime. And now I'm going to just put in the values of these guys that we derived over here. Okay. So these values that we derived from the momentum, quantization, and the winding. So if I do this, then this is going to be 2m squared times, actually, I'm just going to write the final answer, which is very easy to derive, just one line of algebra. So it's going to be n squared by r squared plus w squared r squared by alpha prime squared plus 2 by alpha prime n plus n bar minus 2. Okay, so all of these things are new now. They weren't there when we were looking at the masses in the non-compact space. So, but on the other hand, we have the level matching formula. And the level matching formula tells us that L naught minus L naught bar has to be 0. So if I do this, so I have to take subtract one formula from the other. And if I do that using the value of alpha naught 25 that we just derived, I'm going to get 2 alpha prime n squared by r squared plus omega w squared r squared by alpha prime squared. And then I'm going to have plus 2n wr divided by r alpha prime. And then from the other term, I'm going to get n squared r squared minus w squared r squared alpha prime squared. And then we're going to have a different sign here. So because of this minus sign, that sign is going to flip and become 2 n w r by r alpha prime. And outside, I think there's alpha by 2, alpha prime by 2, plus 4 by alpha prime n minus n prime. And this is going to be 0. Now, a lot of these junk is new because we have a non-compact direction. Remember that this thing in the non-compact space just led to this being 0, this condition. But now we have all this extra stuff, right? So if I now look at all this extra stuff, you see that there's a lot of cancellations. So this thing cancels with this thing cancels with this thing. However, this thing, this goes with this. And then what we are left with is a very simple formula where 0 is equal to NW, because there's an alpha here and alpha, so those two alphas go away. And here there's a 2 and there's a 2 that becomes 4. So that 4 and this 4 cancels out. So we get NW, N plus N bar. So this is the thing that we get from the level matching condition, right? So we have two formulae when we have a compact direction, that is the mass squared is given by this thing. So we will need this formula to figure out what are the massless states in our new uncompactified theory. So this is equation number 2. The equation number 2, 1, and the equation number 2 is that the quantization of the momentum in the compact direction, the winding of the string, as well as the oscillator modes, the number of excited oscillator modes must satisfy this level matching condition. So these are the consistency conditions. So now that we've derived these things, we can ask, what are the massless modes? Because most of string theory deals with the massless modes, because as when we are working with low energy physics effect. So what are the massless modes? Well, in addition to whatever modes we had in our space-time, so remember from Sajid's talk, we had G mu nu, which was the metric, but now mu nu, this just goes from 1 to 24. So it's a metric in the 25-dimensional space-time that is non-compact. And there's the antisymmetric generalization of Maxwell's field. So this is sometimes called the Kalb-Ramond field. So this is the Kalb-Ramond field. And then we had the dilaton. But now we have these extra terms because of the massless modes, because of the compact direction. And what we can do is that we can say, okay, if I take n equals to 0 and w equals to 0, then this is 0. And then we can take n and n bar to be 1. So that is a way of getting uh, getting massless modes. So what are these modes? Well, we've already written the three modes that are coming from the non-compact direction. We can be a little bit more explicit about these. So G mu nu, which is the graviton, the operator that creates them are these guys. These are the creation operators from the left and the right and the left movers. And if you operate them in a symmetric combination on a vacuum state with momentum k, then you get the graviton, right? You get something which has symmetric indices. So for the Kalb-Ramond field, which is say B mu nu, what you do is that you take the same thing, same operators, I should say, sorry, and instead of this being plus, you put a minus sign here, right? So that gives you the antisymmetric Maxwell field. And then if you want to construct the dilaton state, then you say, okay, I'm just going to now create the 25th dimension Okay, so this is going to be the dilaton, right? So this is what we had for the traditional string, and but now we have some extra states. One is we have a U1 gauge field, which I'm going to call U1 left, a gauge boson. And so let's call this A mu left electromagnetic. And that is going to be given by, it's going to have one vector index, space-time. So I need a creation operator with a space-time index, and another index, which is the internal index, the compact index. So this is a space-time vector. So this acts like a U1 left gauge field. But there is a U1 right gauge field. And that is A mu R, and that's just the left and the right mover exchanging places. Okay. So these are the low energy effective fields, the massless effective fields we have. Okay. So maybe this is a good time to take a break and ask if there are any questions.
Yes, sure. So participants, if there's any question, you can type in the chat, or you can unmute yourselves.
So yeah. So maybe I can also like refresh why these things are there. Like yesterday I talked about Kaluza-Klein theory. And there what we did is that we took a 5-dimensional action, which was the Einstein-Hilbert action. So this is the Lagrangian or Lagrangian density. And this is a 5-dimensional Ricci scalar. And we have a five-dimensional space, and Kaluza, Klein, and Einstein said that what happens if I take a four-dimensional Minkowski space times a circle? Then the five-dimensional metric G mu nu can be written in terms of a four-dimensional metric, which I can call G mu prime alpha, and a four-dimensional vector potential, which is like a Maxwell field. So you can write this as a nu prime. So this is a column matrix, and here we have a row matrix, and then you have a 5 by 5. This is the scalar. So the low energy effective action, so then what you do is that you take these fields, say F generically, and you expand them in the extra dimension. You do a Fourier series, and then you take the lowest energy, the massless modes, and if you throw away all the energy to, because of quantization of momentum, the extra dimension will have some quantization of momentum, but the difference in the energy of these momentum modes, they're going to be proportional to the radius of the circle. So if you take the radius of the circle to be very, very large, very small, the energy gap is going to be very large. So as long as you're not doing a very high energy experiment, say of the order of Planck, you won't see the massive modes. So as a result, you'll have a low energy effective theory. So low energy effective theory in which one gets this kind of Lagrangian, where the scalar field dresses the four-dimensional Ricci tensor, and up to signs, which I'm not going to be very precise about, one gets something like this, and there could be. So if you want to, the problem is if you want to get rid of the scalar field here, it ends up being here. So this is not the traditional electromagnetism plus GR. So what we are seeing here is something a little bit different. What we are seeing here is GR and a B field, which was already there in the string spectrum, a dilaton, and because we are doing string theory, we have two abelian gauge fields. Okay, so this is slightly different from what we get from the usual Kaluza-Klein theory. But there are also winding modes that they are not yet visible because they are not yet massless. Okay, because if you remember, I'm taking n equals to 0, w equals to 0, right? So we are not looking at the winding modes so far. We are solving this, and to solve this, we have to take those masses to be 0. Okay, we will soon consider how new massless modes can appear. Okay, so let me carry on. So now what we can do is that we can observe certain things, and which we call T-duality. So if I go back to my expression, I will leave this, so I'm just going to bring this down here. So we see that the masses, in fact, the states are invariant if I exchange N with W simultaneously with, if I say, I'm going to change, I'm going to instead of R, I'm going to introduce a new radius, which I'm going to call R prime, and the new radius will be alpha by R. Okay? So if you do the substitutions, obviously this thing doesn't change, right? Because this just cares about this substitution. And then over here, if I look at this, what do I see? If I exchange n squared, then this n squared becomes omega squared. This omega squared becomes n squared, right? And this r squared is now replaced by alpha by r. So the r goes upstairs, r squared, alpha prime. So yeah, there should be alpha prime. Alpha prime is downstairs, right? So this term becomes this term, and so and this term becomes this term. So what we're seeing is that what it means that physically, as R increases, so as R increases, what happens is that the momentum states become, the quantization between them, the distance between them becomes smaller and smaller. So as R increases and goes towards infinity, the momentum modes in the compact direction, they become continuous, right? But the energies or energy differences, between the consecutive winding modes become larger and larger, okay? Because, they are being stretched more and more. So the winding modes will have more and more energy, right? So this is what happens when R is increased. But when R is decreased, when R is going towards zero, the winding modes become or start becoming massless. And the momentum modes become more and more massive. So we see that these two scenarios are identical if we change the word momentum with winding, and winding with momentum, and R going to infinity with 1 over R going to infinity, right? So at the level of, so the statement is that at the level of spectrum, string theory on a circle of radius R is equivalent to string theory on a circle of radius r prime, where r prime is alpha by r. Now, this is, of course, at the level of the spectrum, or spectra, I don't know what you want to call it, spectra. But one can show by going to a conformal field theory picture that this duality also extends to the interactions, to the full theory. Okay. And therefore, string theory has this duality, and this is known as the target space duality, or more proper, T duality. Okay. So this is quite amazing that because of the extended nature of string theory is blind to a circular direction of radius r and alpha prime over r. Okay. So this doesn't happen in any quantum theory based on particles.
Yes, of course. We have an extended object here.
Yeah, it's an extended object which has a center of mass. The center of mass acts like a particle, but the winding acts like a string, and those two get exchanged when the radius it goes to alpha prime over r. Just one word of advice, warning. Different in some books, you get a +2 here or 2 here, I forget. So, just, difference in convention. Okay. Right. Now, let's see what happens under T-duality. So remember our quantization of the 25th dimensional oscillator modes. So they had, in the presence of winding, in the presence of a compact direction, they had this. This was the right moving and the left moving. Okay. So what happens under T-duality is this 25, this goes over to this. And the tilde goes over to, to minus of this. Okay. Right, because omega and r get switched in such a way that the second one takes up a minus sign. Equivalently, you can show that what was x25 of zz bar, which was x25 of z, and maybe this could be an exercise that you show. This gets exchanged with a new coordinate x prime 25, which is the old x, the right moving, now minus the left moving. Okay. So again, let me just emphasize that T duality, should be small d here, T duality is an exact duality of perturbative string theory. It's kind of it's quite amazing. All right. Now there is a very interesting thing that happens at a certain radius. So remember that r prime is equal to alpha prime by r. What if the value of r prime is equal to r? Okay. So at this point, basically both space-time have the same radius, right? So what is that radius? That radius is square root of alpha prime. This is known as the self-dual radius. All right? So at the self-dual radius, we have some miracles happening. So if I now take this and replace essentially r by square root of alpha, right? Then what are we going to get? In here, replace all of this by square root of alpha. We get so we basically get rid of all alpha, right? So therefore, we get alpha naught 25 becomes n plus w by square root of 2. Alpha naught 25 becomes n minus w by square root of 2. And then we can go and say that, okay, let me look at the mass formula. And in the mass formula, we had m squared, we had 2. So this now becomes n plus w squared plus 4 by alpha prime n minus 1. This is written in terms of the right movers. If we write it in terms of the left movers, so this is from L0 minus 1. And in terms of the right movers, so this is 4, not 1, plus 4 by alpha prime n minus 1. And this is from this equation. Okay. So now we can ask what happens if I set this equals to 0. So we get certain states only when the radius is self-dual. And what are these states? One possibility is that you get n is equal to minus w, and they are either plus or minus 1, right? And also you can get the right movers at site 1 state, the left mover, no state. Or you can say n can be plus. So this is, if you do this, you're satisfying this equals to 0. But if you do this, then you'll be setting this equals to 0. So this is equal to plus minus 1. N is 0 and n bar is 1. Okay? So these are the possibilities of massless modes, extra massless modes that we have when our radius is orbital radius. See that these are not the other massless modes, because the other massless modes had n and w equals to 0 and both n1 and n bar equals to 1. But here we have a completely different set of modes. So how can these modes arise? Okay, so these modes can arise in two different ways. The oscillator excitations, that is these guys, can happen in the non-compact direction. So the oscillator excitations can happen in the non-compact direction. So basically we'll have states like A, the creation operator in some non-compact, and or this. Okay. So we basically have how many states? We have for this guy, we have say 2. For this guy, so these are space-time vectors. Okay. So previously we had a vector boson in the left, but now we have 2 more vectors. So we have 2 new vectors here and 2 new vectors here. So what they can do is that they can combine with the previous vectors to create a triplet of vectors, 3 vectors. And you can show that these 3 vectors now form a joint representation of the SU2 gauge group. As you know, SU2 has 3 dimensions, so its adjoint representation is 3-dimensional. So if you get a non-abelian gauge group representation of SU2, it will have 3 vectors. Similarly, here you will have SU2 left, you get 3 vectors. So we see that, and then, okay, this is the one possibility. The second possibility is that the oscillator excitations are in the compact directions. Okay, compact directions. So, which means that we have a minus 25 acting on this, and a tilde minus of 25 acting on this. And for this, we have no space-time index, so this will be a scalar. But there are 2 of them, And these two scalars can form a Higgs for the, and this can also form another Higgs. So we see that at the self-dual radius, one can have new massless degrees of freedom, which can lead to an enhancement of the symmetry. So suddenly we had for generic value of a radius, we had a gauge group which was U1 left cross U1 right, but at a generic at a special radius, this becomes enhanced to SU2 left, sorry, as well as SU2 right. So this enhancement of the of a symmetry by the appearance of some massless modes is an exclusively string theoretic phenomenon. Okay, and in string theory, this plays a very, very, very important role, and often certain kinds of singularities. So string theory. So I'm just gonna kind of go ahead and like just give you a qualitative description of an interesting phenomena that happens in string theory. In string theory, there you can have this internal six-dimensional space to be things like Calabi-Yau manifolds, and these manifolds are dynamical, so they can fluctuate. And so they can fluctuate in a way that they can even change their topology. For example, this cycle, there's a cycle, this can pinch off, right? And then it can become a different topology, something like this. Okay. So the thing is that this is a singular process by which you pinch off some cycle and you blow up another cycle. But the thing is that in string theory, there are, we shall see, there are strings, but also there are higher dimensional branes which are wrapping around these compact cycles. So when, these things get pinched off, what happens is that this, this extended vibrational modes at zero energy. It doesn't require any energy to excite them. So even though the underlying geometry mathematically is going through a singular transformation, the way one experiences this singular transformation in string theory is that at certain space, at certain values of the parameter space, the parameter moduli space, at certain points on the moduli space, we suddenly have some new massless degrees of freedom appearing. And that mediates a transition between two different manifolds with different topology. So string theory is extremely rich in terms of mathematics, that you can actually have topology transitions in string theory. Okay. Sajid discussed about, and this is related to all kinds of interesting stuff, such as mirror symmetry. Okay, let me come back to T-duality. So, right. So the thing is that we can have more than one dimension. We can have more than one S1, right? We can have S1 cross S1 cross S1. We can have these sort of compactification are called toroidal compactification. Because you're taking your compact space to be a torus, and the toroidal compactification looks, it's a donut. But a mathematical way of describing toroidal compactification is to go to a lattice. So what is a torus? Well, torus is essentially if you take a two-dimensional plane and you have a fundamental vector, right? And then you have a vector which is 1, another vector which is tau. And you can write it as a z-plane. So now if you translate these vectors, what you get is that you get a lattice, right? You get a lattice of like that, right? So you get a lattice. So now if you mod out your space, so this is whatever space, say C, which could be R2. So this is some lattice. Now, if you mod out this, then you get a two-dimensional torus, right? So this is basically, so we can visualize compactification on higher dimensional, on a multiple number of S1 in terms of taking a lattice and then doing a compactification. So doing a modding out by a discrete group, translation group. So what is gamma? So if you take a space which was initially non-compact, you will have some translational invariance, right? So, but if you say, okay, this translation, so this is some vector x. This vector x is just going to be some integer multiple of, let's call this the unit vector 1 and another vector tau, right? So if you constrain your A to be that, then your translation group breaks down to a discrete subgroup. And that discrete subgroup, I'm calling this gamma. And if you identify points up to the discrete subgroup, you get a lattice. So this is similar to saying that if I take the real line and I take 0, 1, 2, the integers, and I identify the integers. So then what we're doing is that we're taking R and modding out by the integers. And that's how we get the circle, right? So similarly, by modding out by a lattice on some non-compact space, we can get a torus. And it doesn't have to be a T2. If the lattice is higher dimensional, we can get Tn, an n-dimensional torus. So now we can extend our string theory computation on an n-dimensional torus. And I won't go into the details of this because it's pretty technical, but it's basically an extension on what we've been doing. But now we have just as we could play with the radius of the, we could play with the radius of the circle, and at a self-dual radius, we had an enhancement of symmetry, that certain similar things will happen on the torus. So at certain radii of the different directions, there will be different enhancement of symmetries. What that enhancement of symmetry will depend on your parameters. But if your torus is Tn, the parameter space itself has a beautiful structure, and it can be shown that the parameter space is given by, I think, SON, comma n. This is the special orthogonal group with a signature NN, quotiented by SON cross SON. Okay. So this is a very rich structure of T-duality that we won't be going into, but I just wanted you to kind of know this. All right. So next, I think I'm going to take 15 more minutes for this lecture.
Yes, that is
next.
perfect.
Yeah, and then I have an exam, and then today we have the next lecture is at what, 5:30 Pakistan time?
5:30 Pakistan time.
Okay, that's going to be 6:30 in Bangladesh. Okay, perfect. All right. So so now the next thing I want to discuss is how open strings behave under T-duality. So T-duality and open strings. Okay. So so before I do that, I just want to kind of do a kind of a diversion on something called Wilson lines or Wilson loops, okay? So maybe that will be, we'll have to wait until tonight's lecture to get into how T-duality is applied to open strings, because this is how D-branes arise, right? So D-branes are actually arise from T-duality. And people thought that, okay, open strings cannot really wind around circles, right? Because they don't have a winding number. If you wind a open string around I don't know, suppose you have a rod, and then you just hang an open string around it, and the wind comes and it'll just take your open string away. It'll just fall off the rod, right? So there is no static configuration on the open string, right? But we shall see that by applying T-duality, open strings can lead to a certain object called D-branes. Okay, but before we do that, I want to introduce an idea called Wilson lines or Wilson loops. And those who are mathematically minded, this is related to, in mathematics, which is called monodromy. Okay. So you're familiar with, say, electromagnetism. Electromagnetism is a gauge theory. It's a U1 gauge theory. So that means that it has a four-dimensional gauge field in 4 dimensions, in higher dimensions will be higher dimensional, which if you do a gauge transformation, which is of this form, the physics does not change. The Maxwell tensor, which is given by this, and maybe there's a factor of half, or maybe there isn't, I don't know, doesn't matter. So if you make this transformation, sorry, was there a question?
No, sorry.
So if you do this transformation, F mu nu does not change. So this is a gauge invariant object. But when we go to some non-abelian group G, non-abelian group G, and you can take G to be, for the sake of argument, to be SU2 or U2, whatever, non-abelian, right? Then the gauge symmetry, this thing now has a gauge index. And if I take the generators of my group T and I contract them, then this is my gauge field now, but now this is a matrix which this thing didn't have. Right. So because it's a matrix, if I take this is no longer zero. Okay. So now if I make a gauge transformation, first of all, what does a gauge transformation even look like? Is going to be A mu prime. Now we are going to have U times A mu U inverse plus or minus, I think it's U du U inverse, something like that, right? What is U? U is a finite element from your group G, right? And because A is a matrix, it does, this is, this thing cannot go through and annihilate U, and therefore this is where, this is the non-abelian version of this. So this is, of course, not a tensorial transformation because this term is not tensorial, and that's why, this is not a, this is a connection. So what happens under this transformation to F mu nu? So F mu nu, unlike, so what is F mu nu? F mu nu in the case of Yang-Mills theory is F mu nu times the generators TA, right? So under this transformation now, it's not hard to show, and Yang-Mills showed it. And I recommend highly anyone who wants to know about this to read the original paper by Yang and Mills. It's a really well-written paper. And this goes to U F mu nu U dagger. Because we are looking at U group, so dagger and inverse is the same. So we can just write inverse here. Right, so we see that this is no longer gauge invariant, it's gauge covariant. And the Lagrangian of Yang-Mills theory has now a trace over this F. So it's F wedge star of F. It doesn't matter if you don't understand what wedge is. Let me just write it in a different way. F mu nu, F mu nu. That's so the trace is over the gauge index, and then there is another term. Here I think it's 1 over G or something, and here there's a theta. It's F mu nu, F tilde of mu nu. What is F tilde? F tilde of mu nu is if you take the 4-dimensional Levi-Civita and you do this. So this term is topological. This term doesn't really contribute to the equation of motion, but it's called a theta term. But in quantum mechanics, we deal with the exponential of the action. So this is going to have an effect, observable effect in the quantum theory. Anyway, What I wanted to show is that this is not a gauge invariant. This is gauge invariant because of the trace. Okay. So the question is, what are the gauge invariant? What are the gauge invariant, observables? Observables in non-abelian gauge theory, or in Yang-Mills theory. This question was answered by Wilson, and the answer is a little bit surprising. Wilson said that, well, if I'm given a gauge field, a gauge field configuration, I can consider what Wilson is now known as the Wilson line or Wilson loop. It's also known as plaquette. This is going to be given by the trace. So the trace is over the gauge index, the group index. An operator P, it's called the path ordering operator, exponential of I, Q, and Q is a coupling constant, and this thing. Okay. So why do we need the path ordering? Well, if you just expand this, you'll get 1, and then you'll get I of Q of A mu dx mu, and then we'll get IQ squared by 2 factorial, and then we'll get multiple, of these things. Now, these things are now matrices. So for different values of X, they will not necessarily commute. So if I didn't have the path ordering here, this exponential would not be, because of this integral, this expression will not be well defined. So that's why we do path ordering, meaning that if A mu X and A mu Y, if they're path ordered, this is going to be A mu X, A mu Y if X is greater than Y, or it's going to be so let's call this A mu Y, A mu X if Y is greater than X. So there's an analog of that called the time ordering, which shows up when we are trying to solve a Schrodinger equation, and when the Hamiltonian is time dependent. And in that context, this solution is known as a Dyson series. Okay, so this is the definition of the Wilson line, and this is gauge invariant. Well, let's show that, why it's gauge invariant. So if I look at, say, this thing, A mu d of dx mu, if I use by using a version of Stokes' theorem, we can turn that into a surface integral, and inside the surface integral, we'll have the Yang-Mills field. And because at some point, this is going to have trace, there can be multiple versions of this. This is gauge invariant. It's the trace. It's a trace that makes the U's go away, and it's this the Stokes theorem that converts A to a surface integral, and therefore this is the Wilson loop, or the Wilson line is a gauge invariant quantity. Now, I have 2 more minutes, and I'm just going to say one thing.
Yes.
If I take my gauge field, suppose this gauge field is in some group at UN, but if I take my gauge field to be such that it's, in terms of the N index, it's only the diagonal elements are non-zero. Okay, we get EI theta 1, EI theta 2 dot 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 EI theta n. So this is a perfectly valid field configuration. In that case, the UN gets broken down to n factors of U1. Okay. And in that case, the path ordering is no longer relevant, and we can get rid of the path ordering. Okay. So I think this is good. Let's end here.
Yes. Yes.
And I just want to kind of like advertise what I'm going to do. I'm going to finish off this debrain in today's lecture, and then I'm going to give you an overview of supersymmetry. And
Great.
because like not really overview of supersymmetry, but it's overview of supersymmetric strings, and because we need that to be able to understand the debrain in supersymmetric string theory. Okay, so that's what we're going to do tonight. Okay.
All right.
So okay, Imran, thank you very much, and we'll see you at